Okay, so welcome back to this next video in which we are discussing Cayley's theorem. Okay, so in the previous video what we discussed is that the composition table for a group has this very special property, which is that for all of the rows of the composition table and all of the columns of the composition table, every single one of those rows and columns contains every element of the group once and only once, basically. Okay, and we are going to use this fact in order to show Cayley's theorem, basically. So let's now actually turn our attention onto what Cayley's theorem is all about. Okay, right. So let's go back to our original motivation. So remember, the group is a set of symbols, okay, one of which is the identity element. Okay, so here is our set of symbols, and on that set of symbols we have our composition law defined. So we know the answer as to what any symbol composed of any other symbol is equal to. Okay, now the question we are trying to answer is it always the case that you can think of the elements of a group as representing set permutations of some set, and the composition law on the symbols of the group as representing the composition of those set permutations that the symbols represent? Well, Cayley's theorem says yes. Okay, so what I'm going to now do is show you the set permutations that each symbol of the group can always be thought of as representing, basically. So you can do this for absolutely any group. Okay, right. So the first thing we need to ask then is, what is the actual set that we are going to use for taking set permutations of? And the answer is we're actually going to use the set which contains the symbols of the group itself. So what you can imagine doing is just duplicating this set. Take a copy of it, basically, and then paste it down here. Okay, but you're just copying the set. You're not taking the full group. You're only taking the set with the symbols of the group in. You're not taking the composition law. Now you've just got a set down here with symbols in. Okay, so this isn't a group. This is now just a set. Okay, so this is the group up here, and I'll just put some colour on this. So we'll have the group represented in red here. Okay, it's the set of symbols with the composition law defined on it. And now I have just copied the set of symbols from the group here to create a set down here. And this is the set that we are going to think of every element of the group as representing a set permutation of. And this composition law is then going to represent the composition of those set permutations. Okay, so what I now then need to tell you is what set permutation of this set down here is each symbol in the group going to be attached to, basically. Which set permutation is each symbol going to represent? Okay, right, well this is where this understanding of the rows of the group comes in useful now. Because basically, I am going to let every element of the group, let's say little a, which is an element of the group, I'm going to let it represent the set permutation, which is going to send any element of the group little g, or I should say any element little g of this set. But of course this set here contains all of the symbols of the group, and maybe it would be better to relabel that up as little s, but since I've already put the little g there, I'll keep it the same. Okay, so it's going to take any element of this set in turquoise here, okay, and it's going to map it onto the element of the set here composed on the left with little a. So it's going to map it onto little a composed with little g. Okay, now, because every element of this set is an element of the group, then you can do this, basically. Okay, you can, in order to work out where it goes to, you can remember back the fact that little g is an element of the group, and then you can ask what is little a composed with little g here, and that will give you some answer. Okay, and that's where little a, as seen as a set permutation of this set, will send any element little g. Okay, so that's how we're going to define the set permutation that is attached to every element of the group, basically. Okay, right. So the first thing to ask is, why is this actually a set permutation? Okay, Well, what do you need to be in order to be a set permutation? You need to be a bijective map from this set to itself, basically. Okay, so what you need to be is, if we draw the set here, so here is our set represented as this circle here, you need to be a map that maps the set onto itself, and this mapping needs to be bijective, basically. So it needs to be injective and it needs to be surjective. Okay, so let's just take on these two criteria here. Okay, well, first the injective. What does injective mean? That means that every element that you are mapping onto over here needs to have just one element being mapped onto it. Now, why do we know that? Well, think what this actually means. Okay, think what this mapping actually really means. Okay, thinking back to what we discussed in the previous video. Okay, so here is little a, and here is the entire group up here. Okay, and you are mapping it basically onto this row here. This is little a, g, basically. Okay, so every element of the group is going to be mapped onto its elements down here in this row, basically, the element underneath it in this row. Okay, now why do we know that that's an injective map? Well, we just proved it in the previous video. We proved that no element of the group could appear more than once in this row, basically. Okay, which means that no element in the group can get more than one element of the domain group here being mapped onto it. Okay, so if I just color code this in, here is our codomain here, okay, and here is our domain here in red. Okay, we want to show, in order to show that this map is injective, we want to show that no element in here, let's say little g, gets mapped onto by more than one element in here. But that's exactly the same as saying that no element of the group appears more than once in here. Because if an element appeared more than once in here, that would mean that there was more than one element in the domain here being mapped onto that same element in the codomain. Okay, so we have actually already proven that this is injective, that every element of the group appears once and only once here. Okay, the only once means that this is injective, basically. Okay, that only one element in the domain here can be mapped onto that element in the codomain. So that's injective. Surjective is the other part of being bijective. Now, surjective means that every element of the codomain actually gets an element in the domain being mapped onto it. Well, that's the other part of what we proved in the previous video. We proved that every element of the group appears in here, which means that every element of the group has some element in the domain here being mapped onto it, basically. Okay, so that means that this mapping is surjective. So because of what we looked at in the previous video, which is that this row here, for any little a that you choose, this row will contain every element of the group once and only once. That means that this mapping is actually a bijection. Okay, it really is just a muddling about of the elements of the group. Okay, it is a bijective map from the elements of the group to the elements of the group, basically. Okay, right, so now what I can do then is I can do this for every single element of the group. I can define this set permutation that is associated with every element of the group. Okay, and just to give you a little bit of intuition concerning this, let's think about what the set permutation which we attach to the identity element would equal. Okay, so I'm thinking about what set permutation would the identity represent. So it would send all little g, is an element of this set here, onto little e composed with that element of the set, basically. Okay, but of course we know that the identity composes with any element of the group, just to give that element back again. So in fact it will send every element of the group onto itself, which of course we know from the fact that if we look at the row corresponding to the identity, it is just an exact replica of all the elements that we've got here in the same order, basically. Okay, so every element of the group is mapped onto itself. So it represents basically the identity set permutation, which is good, okay, because we would like the composition law over here to represent the composition of the set permutations, and we haven't got a hope of that being true unless the identity is mapped, or is associated rather, on with the identity map, basically. So that's good. Okay, right. So, hopefully what you agree now is that what I have done now is I have said, take any element in here, I can define a set permutation that you can associate with every element in here. And I've told you exactly how to do that, and I hope I've convinced you that all of these mappings that you would create for every element of the group would indeed be bijective mappings. That's what we've got to so far. All we have done is said we can do this. We can associate every element of the group with a set permutation of this set, which is a duplicate of the set of symbols of the group, basically. Okay, bravo. Now what we want to do is the big thing. We want to claim, this is our big claim here, that the composition law that we have on the group here, okay, which is already defined, okay, we want to claim that this composition law is the same composition law that you would get if you defined composition according to composition of these set permutations, basically. Okay, so what I could now do is, since I've got all of these set permutations associated with the symbols of the group, I could define a new composition law, okay, on all of the elements of the group, where composition now was defined by composing the set permutations which each symbol of the group represents together, basically, and getting a new set permutation, and then putting in as your answer the symbol that represents that new set permutation. And I want to prove, basically, that the composition law that I have got predefined over here is the same composition law that I would get if I worked it out this way, basically. Okay, so that's going to actually turn out to be true because of the clever way that we have defined these set permutations, basically. Okay, so let's now try and prove this then. Okay, so what do we really want to prove? Well, let's take two arbitrary elements of the group. Okay, so let's take a little a and a little b are elements of the group. Okay, we have the answer to what little a composed with little b is in our original composition table over here. So here is the answer. It's little a composed with little b, basically. Okay, and I'm taking arbitrary elements, little a and little b, as an element of the group. Okay, and this is how I'm going to prove that it holds true for all compositions in here, by just taking an arbitrary one, proving that it's true for an arbitrary one, and therefore saying, okay, this holds true for all of them, therefore. Okay, so I've taken two arbitrary little elements in my group, and I've got this entry in the composition table, which is little a composed with little b. Okay, now what I want to prove is that the set permutation associated with this answer here, little a composed with little b, which is of course the set permutation little a composed with little b, whatever that answer is, and it's some answer within the group, that the set permutation associated with that, i.e. the mapping from this set to itself, basically, is the same as the mapping that I would get if I firstly did b and then did a. Okay, so I want to prove, basically, that this is a of b of g. Now, if you don't understand that, I'll talk you through it a bit more now. Okay, so think what I am trying to prove here. I am trying to prove that these two composition laws are the same. Now, the answer over here is a composed with b. That's the predefined answer. What is the answer over here? Well, the answer over here is the set permutation that, if I want to ask what is a composed with b over here, the answer is the set permutation that corresponds to doing b first and then doing a first, i.e. it's the set permutation a of b of g. Okay, we do b first and then do a first. Okay, and you'd look at this set permutation and then put in there as the answer the set permutation that corresponds to this. If these two are going to be the same, then this set permutation must be the same as the set permutation associated with the answer over there, i.e. a composed with b of g, which is this set permutation, the set permutation associated with our predefined answer over there, needs to be the same as the set permutation that you get by first doing b and then doing a. So this is what we need to prove, and we need to prove it for all little a and little b is an element of big G, and if we can do that, then we're done. Okay, we have proven that these two composition laws are the same. We have effectively proven that the composition law that I have up here already on the group is equivalent to composition of the set permutations that I have just defined all of the elements of the group to be associated with. Okay, so this is what we need to do now. We need to prove the yellow statement here. Okay, so how are we going to do this? Well, it's actually incredibly simple. Okay, we just use our definitions over here. Okay, so let's start off with the left-hand side here. Okay, so what is A composed with B of G? We'll just use the definition. Okay, this is A composed with B, whatever that answer is, composed with little g. So for all elements of our set over here, the answer to where they go is just whatever the answer to A composed with B is, composed with that little g basically. So that's where we'll send all little g basically. Okay, so that's our left-hand side here. Okay, now let's have a look at our right-hand side. So what is the answer here? Well, we firstly need to do B of G. So what is B of G? Well, of course, B of G is just B composed with G. Okay, that's where we'll send all little g under this mapping associated with the element B of the group. Okay, then what is A of B of G? Well, of course, this now just becomes A composed with the answer to B composed with G. And now you see, hopefully, why this is going to work. Okay, so this is where the right-hand side sends all little g. This is where the left-hand side sends all little g. Those two answers are going to be exactly the same because of the associative property of the group composition rule. Okay, so what I am saying is that under these two mappings, A composed with B and A of B, okay, you send all little g in this set to exactly the same place, basically. So these two mappings are identical, and nothing we did here was required A and B to be specific elements of the group. So this is true for all elements of the group, because this associative property is true for all elements of the group, little a and little b. Okay, so what I have just basically shown you is that the composition law here really can be thought of as meaning the composition of these set permutations that I have just defined the elements of the group to represent, basically. Okay, so what I have just shown you, basically, is that if you take any group that you like, you can duplicate the set of symbols that underlies the group. So duplicate the set of symbols, and then you can think of all of these symbols of the group as representing set permutations of this set of symbols, which is the same set of symbols as the group. Okay, how do you define those set permutations? Okay, well, quite simply, you send any element of this set onto what that element left multiplied by the element A is, where A is your element of your group which you're trying to work out the set permutation for. Okay, so that gives every element of the group a set permutation that can be associated with it. Okay, now the big question is, does our composition law here actually respect these set permutations? i.e., is it true that if I look at what two elements composed together is equal to, A composed with B for instance, that the answer there is the same answer that you would get if you thought of this composition as the composition of the set permutations that I've just defined, and I have just proven to you that yes, that is the case, basically. So this is Cayley's theorem, that absolutely always you can think of a group as representing set permutations of the set of symbols that is the group itself. So all groups can be thought of as being as representing, the symbols of all groups can be thought of as representing set permutations of that set of symbols that forms the group itself, basically. So you can absolutely always think of groups as just sets of symbols representing set permutations, and the composition law on groups as representing the composition of those set permutations that the symbols represent. Okay, now, I'm not finished there, however. I do want to raise one final point, okay, because you might now be wondering, well, we looked at how the rows of a composition table obey this lovely property that every element of the group appears once and only once, but you also showed me that this was the case for columns as well. So couldn't we use the columns to also define set permutations of the set that underlies the group as well, and therefore associate every element of the group with a set permutation that way. Wouldn't that work as well? We use left multiplication here. Couldn't we use right multiplication as well? And indeed you can. You can associate every symbol of the group with a set permutation in that way through right multiplication. However, it doesn't necessarily hold true that the composition law here would actually work with those set permutations, i.e. it's not necessarily true that the composition law here will represent the composition of those set permutations that you've just defined. Okay, and we'll go over that in the next video.